Hi friends, in the earlier sections we have seen signals that have been varying in the form of continuous time varying voltage or current, right? So those signals which vary continuously with time are known as analog signals. There are another form of signal also, that is signals can have discrete values also. Look at this. If this is your wave, something like this. This is a pulse waveform actually. Here we are having discrete values, right? So we are using binary digits to represent such signals. If if it is a high voltage, that is we are using 1 to represent high voltage, and for low voltage we are using 0. So these are digital signals. There are something called as logic gates. Logic gate is a digital circuit that follows certain logical relationship between the input and output voltages. Actually, these are the basic building blocks of digital electronics. There are mainly 5 common types of logical gates used. They are NOT, AND, OR, NAND, NAND, and NOR. These are main or commonly used 5 types of logic gates. Now, each logic gate has its own symbol, and each function of each logic gate is defined by the truth table. You'll get to know what is truth table after this video, probably by the end of this video. Truth table shows the possible input logic level, that is that combination with respect to the output logic levels. Okay, truth table Truth table gives the logic between input and output, and it simply helps us to understand the behavior of logic gate. Now let's discuss about the first type of logic gate, that is NOT gate. This is the truth table for it. That is, when you give input as 0, you're going to get output as 1. And when your input is 1, you're going to get output as 0. So what is NOT gate? It is just inverter. That's it. It produces inverted version of input as output. So the symbol of it is this one. This is the symbol of NOT gate. Next type of gate is OR gate. Here, this is the symbol of OR gate. That is, you have two inputs. Observe that. And here you get output. Let Y be the output, and A and B are your two inputs. So if A and B have the values as 0 and 0, your output is going to be 0 as shown in the table. And for respective values of A and B, that is 0, 1, 1, 0, 1, 1, you're going to get output as 1, 1, 1. So what is output? It is nothing but if all the inputs are 0, then you are going to get 0, or else even if one of the inputs is 1, then you are going to get the output as 1. That is OR gate. You can give multiple inputs also, not only 2. You can give more also. So if your inputs are 3, say you give 0, 0, 0, your output is going to be 0. If your input is 0, 1, 0, your output is going to be 1, because at least if 1 is there, that's enough to give output as 1. 1, 1, 0, this is going to be 1. 1, 1, 1, 1. So hope you understood OR gate. Now let us solve a problem. We have to find the output waveform Y for these given inputs. That is, for t less than t1, our wave A, the first input, and our wave B, the second input, is varying in this way. So I'll apply the OR relation. 0 or 0 will be 0. 1 or 0 will be 1. 1 or 1 will be 1. 0 or 1 will be 1. 0 or 0 will be 0. And here it is 1 and 1 again. So these are my outputs. This is my input given. Let these represent the times t1, t2, t3, t4, t5 and t6. So observe this. Before t1, that is when time is less than t1, A was 0, right? So it will be like this. And from t1 to t2, A is 1. So it will be higher. And from t2 to t3, A is 1 again. So it will be like this. And again, A is 0. It will be like this. And 0 again. And 1 again. And 0 again finally. So this is the A wave, input wave 1. Similarly, for B, you can say that 0, 0, 1, 1, 0, 0, 1, right? So 0, 0, 1, 1 and 0, 0, 1 again. This is the wave of B. And finally, your output, that is 0, 1, 1, 1, 0, 1, 1, right? So 0, 1, 1, 1, 0, 1, 1. So this is your final output. You just note that the input waves have been modified to get a different output wave. That is what the function of logic gates. Our next type of logic gate is AND gate. As you see from the truth table, if all the inputs are 1, then your output is 1. If not, for any other case, your output is 0 in these three cases. And this is the symbol of AND gate. This is a straight line. And this is your output. Of course, here also you need two inputs, right? So there will be two here, A and B. And you can give multiple inputs also, that is 3 inputs, 4 inputs. For 3, for this AND of 0, 0, 0, 0 and 0 and 0 will be 0. 0 and 1 and 0 will be 0. 0 and 1 and 1 will be 0 again. Only it will be 1 when all the inputs are 1. Rest of the cases, whatever it may be, it is going to be 0. That's about AND gate. Let us do a similar problem, just we did right. Now we'll apply AND gate, okay? T4, T5, T6. Okay, I'll just write the output waveforms. 0 and 0 will be 0, and here it will be 0 again. 1, 0, 0, 0 and 0 again. So just from T2 to T3 it is 1, and rest of other places it is 0, right? So from T2 to T3 it will be 1, and all other places, at all other places it's going to be 0. So this is my final output waveform. Next comes NAND gate. You just divide it like this, N and AND. So NAND gate is nothing but AND gate followed by NOT gate. So you have to do two operations here. First you have to do AND, and then you have to perform NOT. That's it. So perform, say, let's take this example, the fourth one. 1 and 1 is what? 1, right? First we have performed AND operation for this inputs. 1 and 1 is 1. Again we have to perform NOT for the output of this first operation. So NOT of 1 will be 0. That is what you got as the output. Observe this. And similarly take another operation, this one. 0 and 1, right? First perform AND. 0 and 1 is 0. And NOT of this output is 1. Hence you have output as 1 here. And similarly you have all these things. And here also NAND gate can take multiple inputs. Simple way to remember is that if all the inputs are 1, 1, 1, then you are going to get the output as 0. If any other possibility, anything, then you are going to get the output as 1. Note that. As you see here, if all the output inputs are 1, then you got 0 in the fourth case. Otherwise, in all other cases, you got 1. So if you have 3 inputs, 4 inputs, just follow the same logic. If you have all ones, then you get 0, otherwise 1. That's it. Sorry, that's not it. There is something very, very special about NAND gates. NAND gates are also called as universal gates, because using only NAND gates you can construct or you can make other basic gates. Like using NAND gates, as you see here and here and here, only NAND gates are used. You can get the final output as if NOT gate is used, as if AND gate is used, as if OR gate is used. So you can make an OR gate using NAND gates only. You can make AND gate using NAND gates only. And how is this done? If you are giving same signal for two inputs, that is A and A, first you have to perform AND right for NAND, and A and A will be anyways A, and again you have to perform NOT for this. So A NOT. Finally you got A NOT. This is equivalent to NOT function. And take this case. If you are giving two different signals B, first NAND perform AND for AB, you will get A and B, and perform NOT for it. You are going to get this NOT of AB. Actually AND means product, and OR means sum. This is something like it is a different kind of algebra. It is known as Boolean algebra. You will get to know later when you go into higher studies. For now, even if you don't understand these formulas, you just try to give some values for A and B, 0 and 1, 0, and some values like that. And finally, you try to calculate the output step by step. You will find that the output is given by the truth tables of the respective individual basic gates. That is, if this is acting as OR gate, you will find that the output is given as if there was only OR gate, and here as if there was only AND gate. This is how an AND gate is used for constructing AND and OR gates. So here AB NOT is given as a same input for two input portals of this NAND gate, and finally you get A and B. Okay, as I said before, try to give some values for getting intuition. NOR gate. It is nothing but OR gate followed by a NOT. That's it. So first you have to perform OR and then you have to perform NOT for the result. Take this case. 1 or 1 will be 1, right? So you have to perform NOT for this result. NOT of 1 will be 0. That is your output. Take another case. This is 0 on 1. 0 or 1 will be 1 and NOT of it will be 0. So you got the output as 0 here. Take the first one. 0 or 0 will be 0 and NOT of it will be 1. Hence you got 1 here. So first perform OR and then NOT for NOR gate. And simple way of remembering is that if all your inputs are 0, then you are going to get 1. In any other case, you are going to get 0. Of course, NOR gate also can take multiple inputs, 3 inputs, 4 inputs as you wish. Whatever may be the case, if all the inputs are 0, you're going to get 1. Otherwise, you're going to get 0. Try for 3 inputs and you check some values, you'll get some intuition. NOR gates can also act as universal gates. That is, using only NOR gates, also we can create or we can prepare other basic logic gates. Observe this. When same A is fed for both the inputs of NOR gate, first OR is performed, right? So A or A will be A anyways, and you have to perform NOT for it. So finally you got A NOT. That is nothing but equivalent to a NOT function, that is NOT logic gate. That's here. And observe this one, the third one. A and B are given as inputs. So here first OR is performed, A plus B, and then NOT is performed. So you get a bar here. And if the same signal is fed, OR function does nothing here because anyway you are giving same signal. So after performing OR, you are going to get A plus B bar only, and then this NOT will remove that bar, and finally you are going to get A plus B, that is nothing but OR. So this acts as OR logic gate, this combination of these two NOR gates. And similarly here you have A gate, A signal given into these two inputs and B signal given into these two inputs. So because of NOR function, A or A is A, and you get negative of that, that is A bar here and B bar here. Now NOR function is this one, right? You have to first add the signals and then you have to apply NOT. So here your input signals are A bar and B bar. So your NOR function will be A bar plus B bar whole bar, and this is a standard formula, that is AB, which is nothing but AND. The circuit in which an entire circuit, that is that circuit which is consisting many passive components like RC and active devices like diodes, transistors, etc., etc. If that circuit which is having so many components is embedded or it is made on a small single block or chip of semiconductor, that is known as integrated circuit. In simple terms, your computer chip, this small chip is known as integrated circuit, and its area can be very small, maybe 1 millimeter square or something like that. Now integrated circuits, ICs, can be classified basing on the input signal that they are given. That is, if they are given analog signals, they are known as analog ICs. If they are given digital signals, they are known as digital ICs. Now for analog ICs, the output is more or less proportional to the input. That is, it varies linearly. For digital ICs, they contain circuits such as logic gates inside them. Actually, depending on the level of integration, that is the number of circuit components of logic gates that are present in that particular chip or integrated circuit, they can be termed as small scale integration or medium scale integration or large scale integration or very large scale integration. For small scale integration, the number of logic gates inside that integrated circuit will be less than or equal to 10. For medium scale, it will be less than or equal to 100, and for large scale, it will be less than or equal to 1000. And if it is more than 1000, you call it very large, that is very large scale integration. That's it for now. Keep watching. Bye.